Hello students, welcome to my session. Myself is Vanaja, lecturer in physics from Government Polytechnic Nirmal. Today I am going to explain surface tension, and on the completion of this session you students are able to understand what is surface tension and what are the examples in day-to-day life for surface tension, and a clear explanation on the basis of molecular theory, angle of contact, applications of angle of contact, capillarity and examples of capillarity, then the formula for surface tension based on the capillarity. So these objectives we'll discuss in this session. First of all, matter. What is matter? Matter is nothing but it is anything that has mass and takes up some space or volume, and it consists of in three different states, generally solid state, liquid state and gaseous state. For this property, the surface tension, this is the properties of liquids, whereas for liquids they are not rigid. Water or liquid is not rigid, there is no fixed shape but has some fixed volume, whereas solid has the rigid body and fixed shape and fixed volume, and for gases no rigidness, no fixed shape and no fixed volume. So this is the surface tension is the properties of exhibited by the liquids. So we are concentrating on the liquid state of the matter. And among the molecules there exist two types of attractive forces: cohesive forces and adhesive forces. Cohesive forces, the force of attraction, a force developed between the molecules of same material. Molecules of same material is called cohesive forces. The force developed between the molecules of same material is called cohesive forces, whereas adhesive forces is the force of attraction or force developed between the molecules of different materials or different molecules is called adhesive forces. You can see the slide here, the same type of material there exists cohesive forces, and different materials the force of attraction between the molecules is adhesive forces. So these are the two attractive forces existed between the molecules. For same material, cohesive forces; for different materials, adhesive forces developed between the molecules. Then the molecule, the maximum distance from the center of the molecule up to which the molecular force of attraction is called molecular range. We know that the molecular forces are two types, cohesive or adhesive forces, and the maximum distance from the center of the molecule to which the molecular attractive force will exist is called the range, molecular range. Up to how much distance the molecular force exists from the molecule. Here in the slide there is a molecule at the center, and from that molecule the force of attraction is extended up to some limit only. That region, the total region, is the molecular range. And up to the range, so as the molecule is center, there we can imagine a circle as the molecular center and the molecular range as the radius. We can imagine one sphere, That sphere is called sphere of influence. The sphere of influence nothing but it is an imaginary sphere with the molecule as center, and the molecular range is the as radius. We know that the molecular range is nothing but the maximum distance from the molecule up to which the molecular force exists from that molecule. So here the molecular range and the sphere of molecule is clearly visualized from on the basis of diagrams. You can see the slide here. The first one is the molecular range. There is a certain distance up to which the molecular force exists from the molecule is the molecular range, and here in the second figure there is a sphere and the molecule as the center and the molecular range as the radius. So let us rewind the cohesive adhesive forces. The cohesive force is nothing but the force of attraction between the molecules of same substance is called cohesive forces. Suppose if you observe the water molecules, the attraction forces between the water molecules is nothing but cohesive forces. The attraction forces between the oil molecules or the attraction forces between any liquid molecules. And whereas adhesive forces means the force of attraction between the molecules of different substance, like the attraction force between the paper and the gum. If we stick the paper with using the gum, then the attraction forces between the paper and the gum is adhesive force. And the molecular range of attraction, the maximum distance up to which the molecule exerts some force of attraction is called molecular range. It is in the order of 10 power minus 8 centimeters. What is the range? General range is 10 power minus 8 centimeters. And the sphere of influence is nothing but a sphere, imaginary sphere drawn with the molecule as center and the molecular range as radius is called the sphere of influence. So by using this molecular range and sphere of molecules, we can explain the surface tension on the molecular theory in the next slides. Okay, next the surface tension. So what is mean by the property exhibited by the liquids, that is called the surface tension. So surface tension is nothing but a normal force acting per unit length of imaginary line drawn on the surface of the liquid. So if you observe the surface, first of all imagine a surface, liquid surface, then the normal force acting per unit length of an imaginary line drawn on the surface of the liquid. Just draw an imaginary line over the surface of the liquid. First of all, consider one liquid surface, then imagine one imaginary line on the surface of the liquid. Then the force acting, what type of force? It is a normal force acting per unit length of imaginary line, and this normal force tends to pull the surface in such a way that the surface occupies lowest surface area. This normal force tends to pull the surface in such a way that the surface occupies lowest surface area, and the surface tension is equal to T is equal to F by L. Then what are the units? Newton per meter, and the dimension formula is mLT power minus 2 by L. So it is m power 1, L power 0, T power minus 2. This is the formula. T is equal to F by L, where F is the normal force acting per unit length of the imaginary line and L is the length of the imaginary line. So, and the units are Newton per meter, and the dimension formula is m power 1, L power 0, T power minus 2. So this is the surface tension. Now here also in the slide clearly explaining that the force acting per unit length at right angles means the normal force. That's why we are using at right angles to imaginary line which drawn on the surface of the liquid is called surface tension. So it is force by length. Unit is Newton per meter in SI system, or it is dyne per centimeter in CGS. So this is the surface tension. Now the illustrations are examples of surface tension. So free surface of the liquid behaves like a stretched membrane. If you observe any free surface, constant surface, then it acts like a stretched membrane. So due to this property of liquid surfaces, some insects can walk. Some insects can walk on the surface, or we can a thin needle can float on the surface of the water, and the mosquitoes can lay eggs also. And the raindrops, or if you observe the soap bubble, they are always in spherical shape. Why? Because due to surface tension, there is a pulling force acting on the surface in such a way that they tries to occupy lowest surface area. So among all the shapes, the spherical shape has lowest surface area. So that's why all the soap bubbles or raindrops, if you observe the water sprinkles, water drops in the winter season, they are in spherical shape. Why? Because they tries to occupy lowest surface area due to the property of surface tension, due to the pulling force. There are always acting some force normal to the imaginary line drawn on the surface of the liquid, and tries to pull that in such a way that they occupies lowest surface area. So the surface acts like a stretched membrane. That's why. So let's see here. So the needle is floating on the water surface, and here the mosquitoes, see, the surface is straight, acts like a stretched membrane. So this insects can walk on the surface. And here observe the water bubbles here. So these are in spherical shape. So see spherical shape, and some insects can lay eggs also here. See, the insects lay eggs on the surface of the liquid due to surface tension. So in this winter season we can observe this on the leaves. So on the leaves the water bubbles are occupies spherical shape. So spherical shape. See water raindrops. So if you observe the raindrops, these are also spherical in shape. See, the thin needle can float, the insects can walk, and raindrops are spherical in shape, and the insects can lay eggs. So due to the property of surface tension. So here if you observe the brush here, when we put the brush into the water, the hairs of the brush will spread out, and when we take it out, they are linked together. Why? Because due to capillarity. So due to the capillarity, we will discuss in the next slide here. So these are the some examples of surface tension. Next one, the molecular theory. And the surface tension can be explained on the basis of molecular theory. So to explain this, I am considering one beaker. So here there is a beaker here, and pour some water on in the beaker, and here PQ is the free surface of the liquid, and just I am considering three circles, means three molecules. Three molecules are selecting in the surface, on the surface, and the sphere of influence is A, B, C, I am considering one molecule, and around the molecule take a sphere of influence. And what is the sphere of influence? The sphere of influence is nothing but a sphere with center as a molecule and molecular range as radius is the sphere of influence. So I am considering three molecules, and around that there is sphere of influence. The A, B, C are the sphere of influences. Okay, sphere of influence of molecule A, B, C. And what are the positions of the A, B, C here? Where the A is completely inside the water, and B is some part of the sphere is above the liquid surface, and remaining all part is inside the liquid surface. Whereas for C, C is half portion of the sphere of influence is outside the is above the liquid surface, and remaining half part is below the surface, means below the liquid surface. So these are the positions. A is completely inside, and in the B means only small portion is above the liquid surface, and for C half of the portion is above the liquid surface. Here why we are considering three different sphere of influence at different positions means what is the resultant net amount of force acting on the molecule. We know that for the molecules there are molecular force of attractions that are existing, that are cohesive forces or adhesive force. So here water molecules we are observing, so the cohesive forces are existing between the molecules. So for a molecule it is completely inside the liquid surface, so therefore the molecule A molecule is completely attracted in equally attracted by the molecules which are around the molecule A. So A molecule is equally attracted by the molecules which are existing around the molecule A. So the resultant force is equal to 0. Why? Because suppose the particle means the molecule is A is placed inside the surface. One molecule pulling outside, one molecule is pulling downward direction, and one molecule is pulling in right hand side, and one molecule is pulling on left hand side. So in this way the totally it will be attracted equally in all directions, so that the resultant force is on that molecule is completely 0, means the resultant force acting on the molecule A is equal to 0. Why? Because equal forces, all the molecules existing around the molecule A is attracted. So, and for B molecule, so only some portion is above the liquid surface, so therefore it experiences a resultant force vertically downwards. Some resultant force acting in vertically downward direction into the liquid. Whereas for molecule C, it is just the surface of the liquid, half of the sphere of influence is above the liquid, and thus the molecule on the surface of the liquid experience maximum vertical downward force. So here the net amount of force acting on A molecule is 0, whereas there exists some resultant force on B and C. By comparing these two, only B is a small portion is above the liquid, whereas for C half of the portion is above the liquid. So that's why maximum net force acting on the C in downward direction is more for C compared to B. So the maximum vertical downward force acts on C, whereas for B it is somewhat less. Why? Because only small portion is above the molecule. So if a molecule from the interior of the liquid is brought into the surface, work is done against a downward force, and its potential energy is increased. If a molecule from the interior of the liquid is brought to the surface, work is done against a downward force. The potential energy increases. This indicates that molecules on surface possess greater potential energy than those inside the liquid. The molecules on surface possess greater potential energy than those inside the liquid. Hence, the liquid surface trying to have least surface area. This tendency of free surface of the liquid at rest to have minimum surface area is called surface tension. So, these tendency of the free surface of the liquid possess minimum surface area, which is called as surface tension. Here, the potential energy of the molecules which are existing near the surface is more compared to the molecules which are existing inside the liquid surface. So here, then we go for angle of contact. What is the angle of contact? Suppose, observe the two beakers. One beaker is filled with water and another beaker is filled with mercury, like this. See the slide here. If you observe the shape of the surface, it is concave. It is concave for water. If you observe the edges, the shape of the water surface at the near the edges, they are concave in shape, whereas for mercury, it is convex. It is convex. Observe the surface of the water near the edges. It is concave. Here, mercury, it is convex. And I am just insert one capillary tube into the beaker. I am inserting one solid body. That solid body is a capillary tube. Inserting into the, we are dipping inside the liquid. Then when the solid body is dipped into the liquid, the angle between the tangent drawn to the liquid surface and the solid at the point of contact measured inside the liquid is called as angle of contact. So, first of all, draw a tangent at the surface of the liquid near the solid surface. Then the angle between the tangent drawn at the surface of the liquid and the solid surface inside the liquid is called as angle of contact. So here also the tangent drawn on the surface of the liquid and the angle between the solid body and the tangent drawn at the surface of the liquid is called angle of contact. Here the angle of contact may varies for water and mercury. It is in between 0 and 180. So for water it is less than 90 and for mercury it is more than 90. So for angle of contact depends on the nature of the water and the solid body, means the solid body means it is glass, it's made up of pure glass or not. So the angle of contact between the pure water and pure glass, it is nearly 0. The angle of contact is nearly 0. And for pure mercury and pure glass, it is around 140 degrees. 140 degrees. So the angle of contact is a angle between the tangent drawn at the surface of the liquid and to the solid body inside the liquid is called as angle of contact, and it is in between 0 and 180. For pure water and pure glass it is equal to 0, and for pure water and pure for pure mercury and pure glass it is around 140 degrees. So and we have to learn about the angle of contact. First of all, draw the tangent on the surface of the liquid. Then the angle between the imaginary line and the solid surface inside the liquid surface, inside the liquid, is treated as angle of contact. So by knowing the angle of contact, we are using the some liquids as wetting agents and some used as some detergents. Okay, so here the hot water used for washing clothes, and we are generally to clean the clothes we are using the detergents. So we use detergents to clean the clothes effectively, or we can go for hot water. Why? Because the temperature means hot water, if we use the hot water, as the temperature increases the angle of contact decreases, and also if we add the detergent to the water the angle of contact is decreases. So once we add the detergents to the liquid or water, what happens? Angle of contact decreases, so they can easily wet the clothes. The detergent water can easily wet the clothes. Why? Because angle of contact is decreasing here, so they can easily pour into the water. They can go in very effectively into the pores of the cloths and remove the dirt very effectively. So that's why we are using the detergents. If you use only water, we can't clean the cloths effectively. Why? Because the angle of contact is more compared to detergent water. Now, ordinary water and the detergent added to the water, there is a lot of difference in angle of contact. And for we uses some waterproofing agents also. If the angle of contact is more, we can use that liquid as waterproofing agent. So we go for some bags or some shoes, we generally use waterproofing agents. So if we add that waterproofing agents, then the angle of contact is more, but then the water is difficult to wet that material. It is difficult to wet that material. Why? Because the waterproofing agent is added. Okay, so and generally waterproofing agents are used in paintings houses, in paints. If you Why? Because the angle of contact is more, so easily we can paint the house. So these are the applications. By knowing the angle of contact, based on that angle of contact we can use a waterproofing agent or wetting agents depending on the situation. So where we can use as waterproofing and where we can use water wetting agents. Okay, next one, the capillarity. Capillarity means the rise or fall of the liquid due to surface tension. The rise or fall of the liquid due to surface tension is called capillarity. So what is the rise and fall in the capillary tube? So if you observe the water taken in a beaker and we are dipping one capillary tube inside the water or inside the mercury, we are observing two beakers. One is filled with water and another one is filled with mercury, and here the capillary tube is dipped into the water. So then what happens here? The water can rise into the capillary tube, and if you observe the rise means the height of the water level, height of the liquid in the capillary tube in for first water beaker, then the rise, the height of the liquid in the capillary tube is more compared to water level in the beaker. Whereas for mercury, the height of the liquid in capillary tube is less compared to the height of the mercury in the beaker. Means there is a fall in the capillary tube. Whereas for liquid there is a rise in the capillary tube, and there is a fall in the capillary tube for mercury. So the rise and fall of the liquid in capillary tube based on the surface tension, due to surface tension. So if we observe the narrow capillary tube, then the height is increases. The height of the liquid is increases. If we dip the narrow capillary tube inside the liquid. So generally capillarity means the rise and fall of the liquid in capillary tube. And where we use this capillarity and where we observe this capillarity in my day-to-day life. So here the examples of capillarity. So the wax, in a wax candle, molten wax rises up and rises up the wick by capillary action. The molten wax rises up the wick by capillary action. You can see the slide here. So the molten wax rises up by the capillary action only. And the plants, for plants, if you pour some water, the water rises into the stem and leaves due to the capillary action. So due to capillary action only, the leaves and stem can absorb the water. There is a rise in the water, means capillarity. The water rises into the stem and into the leaves by the capillary action. And if you observe the kerosene stove, kerosene lamp, the kerosene rises to the top of the wick through narrow spaces between the threads by capillary action. Okay, and when a blotting paper kept on the ink rises up the paper through the pores of capillary action, due to the capillary action. Then so these are the some examples of capillarity. So and if we dip the brush into the water, then the hairs of the brush will spread out, and if we remove the brush out of the liquid, then they cling together due to surface tension property. So these are the some examples of capillarity. So the wax candle, the wax can rises up by the wick due to capillary action, and in plants they absorb, or the water rises into the stem and leaves due to capillary action only. And in a kerosene stove, the kerosene rises up to the top of the wick through the spaces between the threads due to capillary action. And the blotting paper kept on the ink drop, the ink rises up in the paper through the pores of the capillary action only. So these are the examples. And the formula for surface tension based on the capillarity. So here, to explain this formula, consider one beaker with water, some liquid, and pour one capillary tube, means dip the capillary tube inside the liquid. Then there is a rise in the liquid. So here the capillary tube of radius r is dipped vertically in the beaker and containing liquid of density d, and let h is the capillary rise. H is the rise of liquid in capillary tube. And here we are considering pure glass and pure water. Then 0 is the angle of contact with pure water and pure glass. So according to based on this capillarity, the surface tension is equal to HR dg by 2 cos theta. HR dg by 2 cos theta. What is H here? H is the rise in the capillary tube, rise of liquid in capillary tube, and R is the radius of the capillary tube, D is the density of water or liquid. G is acceleration due to gravity. Acceleration due to gravity. And here theta is the angle of contact. And for pure water and pure glass, theta is equal to 0. We get cos 0 is equal to 1. Means the formula can be written as HRdG by 2. HRdG by 2. T is equal to HRdG by 2. But general formula is H plus R by 3 RdG by 2 cos theta. Where we use this formula means if the surface of the liquid in the capillary tube is convex and H to be altered, so it is convex for mercury. For mercury, if the surface of the liquid in the capillary tube is always convex, so H can be changed that as H plus R by 3. We have to add R by 3 in addition to H. So H plus R by 3 R dG by 2. So 2 cos theta. So here theta is depending on the liquid and glass. For pure water and pure glass it is 0. For pure glass and pure mercury it is around 140 degrees. So this is the formula for surface tension based on the capillarity. What is the formula? It is HR dG by 2 cos theta, where H is the rise of the liquid in capillary tube, R is the radius of the capillary tube, and here D is the density of the liquid, G is acceleration due to gravity, theta is the angle of contact. So finally in this session we'll discuss so many topics. Surface tension. What is surface tension? It is nothing but the normal force acting per unit length of the imaginary line drawn on the surface of the liquid. It is T is equal to force by length. The unit is Newton per meter or dyne per centimeter, and the dimensional formula is mLT power m power 1 L power 0 and T power minus 2. So and the surface tension examples in day-to-day life, we discuss some examples here. And some insects can walk on the surface, and the surface of the liquid acts like a stretched membrane due to surface tension properties. So some insects can lay eggs also, and the needle can float, and the water raindrops are spherical in shape, and water bubbles if we see in the winter season, they are spherical in shape. Why? Because they tries to occupy lowest surface area, so that's why they are in spherical shape. The sphere has lowest surface area. And then we discussed angle of the surface tension explained on the basis of molecular theory. For that we consider three different molecules, three different positions at three different positions. One is completely inside the inside the liquid surface, and one is some small portion is above the liquid, and for third sphere of influence is half of the portion is above the liquid surface, and half of the portion is inside the liquid. So here from this molecular theory we comes to know that the net amount of force there is a net amount of force is acting in downward direction. Net amount of force is acting in downward direction, means inside the liquid. So the potential energy is more for the molecule which are existing near the surface. Next, the angle of contact is the angle between the tangent drawn at the surface of the liquid and the solid surface inside the liquid. is called angle of contact. It is in between 0 and 180, and it is 0 for pure water and pure glass, and it is 140 for pure glass and pure mercury. And to wet the cloths easily, we have to decrease the angle of contact. So that's why we use the some detergents. So the detergents are called as wetting agents. Soap, water, detergents are called as wetting agents. So suppose if we add these waste soaps or detergents to ordinary water, then the angle of contact is decreases, very much decrease in the uh, angle of contact, so they can easily wet the cloths. And these based on the angle of contact, some of the materials acts like waterproofing agents. Waterproofing agents are, if we use the waterproofing agents, then we can't wet that easily. So generally we use for the manufacturing some bags, shoes, um, some cloths, we use waterproofing agents in rainy season. So angle of contact is more for that materials. And so these are the applications here. Wetting agents added to color solutions, detergents added to water for washing clothes, um, and waterproofing agents, hot water used for washing clothes. And here some capillarity. Capillarity means the property of rise or fall of the liquid in the capillary tube, and due to capillary action only, we are observing so many examples in day-to-day life. So they are means the plants can absorb the water due to capillary action only, and the candle, the molten wax can be raised up due to capillary action. And the kerosene, in the kerosene stove, the kerosene can rises through the wicks of the uh, narrow spaces, through narrow spaces due to capillary action only. And when blotting paper kept on the ink drop, the ink rises up to the paper and through the pores of the paper due to capillary action. And finally we discussed some formula for surface tension based on the capillarity. So for that I am just dipped the capillary tube of radius r inside the into the liquid containing in a beaker. So the density of the water is d, and r is the radius of the capillary tube, and h is the rise of liquid in capillary tube, and uh, g is acceleration due to gravity, and theta is the angle of contact. Then the capillarity, the surface tension T is equal to HR dg by 2 cos theta. For here theta is the angle of contact. If we take pure water and pure glass, theta is equal to 0. So cos 0 is equal to 1. Whereas if we take the pure water and the mercury, then there is a fall of liquid, and we have to take the rise fall in addition with r by 3. So h plus r by 3 r dg by 2 cos theta. So this is the formula for surface tension based on the capillarity. So here the formula is h plus hr dg by 2 for theta is equal to 0 and cos theta is equal to 1. So we get hr dg by 2. And for if the surface is a convex, where we get convex surface for what? Mercury. For mercury and solid surface there is a convex shape. So the h can be altered as h plus r by 3 into r dg by 2 cos theta, and if theta is depending on the solid surface and the mercury. So in this session that we completed, so surface tension topic, means the surface tension examples, explanation based on the molecular theory, angle of contact, applications of angle of contact, capillarity, and the examples, and finally on the formula based on the capillarity. So go through this PPT and get the knowledge. Hope this very good gives very good information for you students. Thank you one and all.